So my dear student, colleagues, and all the viewers who are watching this program live from Facebook and YouTube channels. So I'd like to welcome you all to our International Physics webinar. So good afternoon to all, and a very good morning to all those who are watching this program live from UK. So hope you are well and safe from Corona pandemic. So as we know that we are staying in a Corona pandemic situation, so it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including International Physics webinar. And we have successfully completed our 160th International Physics webinar, including 2 Nobel laureate speakers. And today it's our 161st International Physics webinar. So we are trying to adjust with this new normal situation. I think you have already come to know that today our speaker is Dr. Garry E. Hunt, Professor and Chairman, NED, and International Business Advisor, UK, and International Scientist, member of NASA, JPL Caltech, USA. So, and I think you have already know about him. So before going to him, I'd like to say something about our speaker. So Dr. Garry Hunt was the only resident of UK scientist selected by the NASA at start of Voyager mission in 1972. His Voyager activities and those with other NASA planetary and climate mission were the basis of major research group he created at UCL and later the Imperial College. Garry is a past president of IAU Commission, International Astronomical Union, 16, the planets, the Commission of Planetary Atmosphere and their Evolution. The chairman of the Space Society and the founding member of the Planetary Society, where he has been a member of the advisory board for 40 years. In 1990s, he moved from academia to business, becoming a CEO, executive director of several major companies. For example, Logica and ICL, a non-executive director and advisor of FTSE and a Fortune company government. Garry has been a regular broadcaster all over the world and continues to speak about the space exploration and climate change to schools, scientists, or other organizations. Garry is a freeman of the City of London and liveryman of the Horseful Company of the Information Technology and has been awarded the Queen's Jubilee Medal for his work in local communities. So thanks for all of your patience. Now it's time to go to our speaker. So sir, welcome to our International Physics webinar, and it's my pleasure and privilege to host you in our International Physics webinar, sir. You can start your session, sir.
Well, thank you very much. And I'm now going to try and get my own system up on board. Hopefully it is, and I will go into play. Whoops, into play. All right. Okay. Whoops. Let's go back one. Well, thank you very much for that wonderful introduction. It's a delight to be talking to you. I wish I had some of your heat. It's cool in Britain. If you're interested in weather, you should be interested to know this is the coldest May since 1967, having had the driest and coldest April since about 1937. So we are having strange weather. So one of the things I want to talk to you about is a little bit, which will show my background and where I came into it. I'm not an astronomer. I read mathematics, and I came into physics later on. But my research side was very much to do with weather and climate. I've always been fascinated by the weather. I wanted to understand how our climate was developing. And I was one of the early predictors of climate change and the things that you're suffering and we're suffering too. And therefore, that was my drive. And I looked around and I realized that there were many planets in our solar system that had dramatic atmospheres, exciting features to look at. And I thought to myself, surely we can learn from them. So today I want to talk about the meteorology, the weather, the climate of the other planets, which are dramatic. But as you can see here, a still picture doesn't tell you much. It shows you the picture of the Earth taken over the Southern Atlantic. You can see South America, Africa, and the United States. But let's go and look at it a different way. This is if it actually works.
Hello.
This is a genuine movie made out of satellite pictures, and I'm going to go to about here. Whoops. And hang on, let's get this to work properly. Oh dear. Ah, I have blown it. Can I go back and can I do my start again?
Yeah, you can stop share and
Right.
do it again.
Hello, and
Right.
welcome to the
That's great.
year of.
I want to show you this. This is a set of satellite pictures taken from satellites of the Earth, made it into a movie, and it's a movie for the whole year. And I want to show you this to show you just how complicated our weather systems are. It names all those wonderful cyclones that move over in your part of the world. And I know you've got some shockers in your part of the world at the moment. You can look along the equatorial region and see the storms there, the storm systems moving north. But the things that you notice is that there's certain local areas of activity. There are features moving towards the pole, and it's very, and these are features which are governed by what's underneath them. 75% of our planet is covered in water. We have continents, all of which will affect and constrain the weather systems. You see the looping around at the mid latitudes, the jet stream. It's that movement of the jet stream which has changed our weather now. We are struggling to be able to give good weather forecasts, to give good climate predictions. It is difficult. And the question that I asked myself was, could we look somewhere else to actually understand how these weather formations formed under different circumstances? Are there natural laboratories in which we can do that? And the answer is yes, there is. Those natural laboratories are without doubt these set of planets, the giant planets, Jupiter, Saturn, Uranus, and Neptune. They're huge. Jupiter is 11 times the size of the Earth, Saturn almost as big, Uranus and Neptune smaller. They're not like objects that we have here. We cannot stand on the surface. They're totally gaseous. They are really like, Jupiter is almost like a failed star. Jupiter and Saturn give out more energy than they receive from the sun. So these are very ancient, early developing models, hydrogen and helium atmospheres, but they have dramatic weather systems. And what we're going to look at is how these weather systems behave, what we have learned, some of the basic questions it leaves us with that we will need to understand, which are helping us to understand our own Earth. In physics, we like to look at the spectra. We like to understand what features are made of. These are radiometric scans made by a microson interferometer by Rudy Hanel, the very distinguished Austrian-American physicist. The instruments have all been flown on different space missions. You can see the Earth. You can see the big absorption feature due to carbon dioxide, the features due to ozone. Mars, a very strong carbon dioxide effect at 15 microns. Now look at Jupiter and Saturn. And you can see the presence of hydrogen, the features of ammonia, acetylene, and then the features of very tiny features, perhaps of water somewhere in that in the atmosphere. Remember, these are looking at the emissions coming from the thermal infrared. This is the heat energy which is being emitted by these planets. And from these spectra, we can see immediately that Jupiter, Saturn, and onward down to Uranus and Neptune are very different from features that we have here. These are primordial atmospheres composed of the features, the early constituents that made up the Earth. So the very strong carbon dioxide features of the Earth and Mars are apparent, and similarly of Venus too. Now, with Jupiter and Saturn, these first of all, the evidence of ammonia and methane and so are a clue that says these are going to be very different. The chemistry is going to be different of what actually takes place. The atmospheres we only see the atmosphere. It goes on and on and on, right the way down to inner core. We have a stratosphere, and then we have the tropopause into the troposphere itself. There will be layers of clouds, and these won't be seen nice white clouds. These will be extremely colorful clouds. The first highest, thinnest ones will probably ammonia, and they will be probably crystalline, have crystals in it too. So we should expect thunder and lightning, which indeed has been found. Although it shows in that picture the presence of water, we actually don't know where the water is and what the water abundance is. And that's important because the power that drives our weather systems on the Earth is through convection, water convection. Saturn has a less steep gradient through its troposphere. You may say, well, how have we got these temperature gradients? Well, I showed you those spectra, and the techniques that we can actually use from Earth satellites is remote sensing, looking at the emissions at different features within the Earth CO2 band, and we can build that up to gain the information on the troposphere. We can do similar things, not in the CO2 band, but in methane bands within Jupiter's atmosphere and Saturn's atmosphere, and gain some information about the emissions and therefore the structure of this lower atmosphere. How far we can penetrate, that's one of the unknowns, and we'll have some clues later on. This is Jupiter. It is, to my mind, the most beautiful object in the solar system. You can't doubt it. But what's the first thing you notice? Go back and think about that picture of the Earth. We could see the continents, and we could see the clouds whirling around and discrete storms. This is a mass of storms. That red spot, it's been there probably since the 17th century. It doesn't stay the same size, as you'll see, and you can see it around the equatorial regions, the great white band, and there are loads of little storms breaking out. It is a mass of cloud features. The white dots, again, giant storms. And the idea of size, the red spot at the time this picture was actually produced, is 3 times the size of the Earth. These are giant features, convective features. And if you take your eye further and further up towards the polar region, the banding disappears, but you can see discrete features. So the first thing that we've said is we look at these giant features, a planet which spins in just about 11 hours. It is about 11, 12 times the size of the Earth. It is colorful, composed of hydrogen and helium, and then the primordial gases to give the chemistry of the color. But if I want to understand the weather, I can't do it by looking at individual picture. I was very fortunate, as you heard, to be involved in Voyager. It was my career. My career started in my late 20s, and we went on and we built this spacecraft that went on to fly by the outer planets. And we built up this spectacular movie. Just watch it. Watch the clouds whirling around the great red spot. The red spot is moving at about 100 meters per second. Features are whirling around. 2 or 3 days is the rotational period of the red spot. Underneath it are the white ovals. And notice how the belts and zones are going opposite direction. You've got very bright features around the equator. They are giant plumes, like those convective systems, like the typhoons that you have. And you've got the dark dots you see further up, and look at as far towards the top as you possibly can. You can make out some more discrete storms. It is the most dramatically exciting feature of all. The red spot is somehow a barrier, but the question you should be asking yourself is, how does it get there? Why does it last so long? The white ovals disappear within time. They don't last so much of a feature. So the red spot is gobbling up other features around it. You can look at the planets in different wavelengths. I've showed you the spectrum, where you can look at it in the thermal infrared at the methane band, and that's what we have. The left-hand side is looking at the emission picture of Jupiter taken at 4.7 microns. What is very bright is high, what is dark is low. So what you saw in that moving cloud movie were cloud systems at different levels. Those bright features around the equator were giant convective storms moving around. You can see the red spot and the high features around it and the low elements around that anticyclonic storm. The other two, the right-hand corner is one taken in the violet, and in the bottom right-hand corner is that one taken in the visible light. Now, the whole purpose of taking it in different wavelengths is that because of the different gases in the atmosphere, you're getting absorption at different levels, and it would start to tell you about the structure. So immediately you can see it's a very well structured atmosphere, in the same way as we have cells like the Hadley circulation around the equator, the Ferrel cell moving towards the pole. These belts and zones are their own little cellular structures whirling around at great speed because of the rotation of the planet. And you can see the left-hand picture shows you 3 white ovals. There's not always 3 white ovals. There can sometimes be 2. They can sometimes coalesce. You have dramatic storms in the tropics, and you have terrifying ones which come up the Bay of Bengal. Sometimes they merge together. That's exactly what you're having here. These storms are merging. And the right-hand picture shows that long, tenuous trail that actually is turbulence within the cloud features themselves. But things don't stay the same. These are 2 pictures not taken from a spacecraft. This is taken from Hubble, which is the telescope which is in orbit around the Earth, to be replaced by the Webb telescope shortly. Shows you Jupiter a year apart. And just flick your eyes from one side to the other. They are in the same longitude, and you can see, my goodness, what a difference. First of all, the banding has changed structure. So there's been disturbances within the atmosphere, which has changed the colors, changed the chemistry, because all this whirling around is mixing up the ammonia, the methane, and all the other acetylenes and ethanes and goodness knows what else is muddled up it within the atmosphere, and altering the chemistry. And it's changed, the band structure has changed dramatically. The spots are suddenly altered. The white ovals have moved apart. There is a large white feature down towards the south, which is stretched out. The northern part has suddenly not become banded, it's become flattened out. So we have weather, we have the change of the situation from one to the next, and so do they. Now, if you look at the red spot area, again in different wavelengths, this one is taken from a telescope in Hawaii, which is called the Gemini telescope. Again, you can see the dates, they're quite recent. You've got one at the bottom, which is involving the red, the green, the blue, one in violet, then at 4.7 microns, the 4.7 micron at the right-hand corner. And the first thing you notice, there's a lot of structure in these clouds. They're anticyclonic, they rotate very fast. Clouds are whirling past at more than 100 meters per second, but there's structure in it. It is not just an obstacle, it is, I almost use the term, self-generating. It gobbles up sometimes features that move past and is able to replenish it. It is actually a very strange object. I discussed this sometime with a colleague of mine whose name you will probably know, Richard Goody, who actually will be 100 in a few days' time. And Richard actually gave it what I think is the best title ever. He called it A Whirlpool of Emotion. There have been many attempts to try and explain it, but we don't know how far it extends. Indeed, how do the motions on Jupiter, how far do they extend? And this intercomparison will be strange. But again, if you want to understand what's going on, let's watch. You can see the clouds at the bottom whirling around, the red spot coming past, some being gobbled up by it, others, the white ovals trying to come along, some creatures to the left-hand, in the left-hand bottom corner, the white oval, you can see a cloud system generating and disappearing in just a few days. This shows you the dynamics, the interactions of what's taken place. It is such a pity we've never been able to put a probe yet down into that area, it will be stunning. But it really is like a whirlpool, like a catering wheel, spinning like crazy, gobbling up what's around it, acting as a barrier for weather systems coming the other way. This is a truly dynamic environment. If you look at this sequence of pictures, which taken us over 3 years, you can see that the white oval DE, BC, they gradually amalgamate. If you look back over history, and in fact, the wonderful book by Peake and the other amateur observers, this is what you can do with your own telescopes in Bangladesh. You can actually track these things regularly. You can see these larger features do coalesce. And then they can, the weather environment can be such that it will generate and spontaneously and create more features. It is an environment which is forever changing. But there was a fortune of good luck. Do you remember many years ago in 1994, there was a comet called Schumacher-Levy, and it did something which was wonderful. It happened. It actually, it had a major collision and loads of fragments broke off, and they crashed very conveniently into the atmosphere. 22 of these tiny fragments came into Jupiter. And in fact, over 6 days, they were bombarding the planet and leaving their mark. Why are they colored, you say? Why are they different? Well, just think, they hit not at a gentle speed, they were actually traveling at an enormous impact of more than 20,000 miles an hour. They actually caused the atmosphere to heat up. We think by about 30,000 degrees. The material burst high into the atmosphere, about 3,000 feet above the cloud deck. It changed the chemistry. It was able to mix up material which is much, much deeper in the atmosphere, and it's left its impact. But the other interesting thing was, yes, it led this sequence of features around the planet itself, but in time, rather like our mothers at home stirring the cooking pot, Jupiter stirred it up and it went back to being itself again. So there has been one impact. There has been a probe, of course, into the atmosphere from the Galileo mission. And they have told us a little about what is going on deeper down. So Jupiter has strange motions, very dynamic, very broad belts and zones. Now look gently at Saturn. Saturn doesn't look so attractive at first sight. You can see the belts and zones, not so many, not so, so obvious features in the atmosphere. Look at the polar regions as well, because here is a chance to see that differently. But if you want to see what happens over a few years, watch this. Notice how the belts and zones are changing in brightness. This is taken from a sequence out of Hubble over about 2008 to about 2011. It's not a continuous sequence, that's why it's a bit jittery. But look at the belts and zones. They change from being wide to narrow to bright to dark. The polar regions start to show up. And look at very carefully at the polar region. You'll notice it seems to form a strange shape, hexagonal. You think a hexagon at the pole of Saturn? Well, that was actually first seen in the 80s, and one of my graduate students, David Godfrey, that was a major part of his PhD thesis. So wonderful things you can do as young students, and you can actually look very carefully. You're going to watch. You can actually see cloud features breaking out within Saturn itself. So Saturn is dynamic. It has interesting cloud features. The belts and zones are broader. It doesn't appear quite as active as Jupiter. It emits roughly about the same amount of energy as Jupiter does to the sun. Its winds actually are faster, whereas Jupiter was about 100 meters per second at the equator. Saturn was actually slightly quicker. But here are some examples of some of the cloud. The left-hand corner was taken by Cassini. And what's extraordinary about this, if you look around about halfway across that cloud feature, that is the tail trying to catch up with the head. It's actually circumnavigated the entire planet. Look at the right-hand corner. You can see a wave line. That's a pure, beautiful example of a baroclinic wave in an atmosphere. A beautiful example. There's another example in the lower right-hand corner. Please don't think these are the colors. These are some examples that we did with Jupiter, where we actually took reds and greens and blues and so on to mix it up, to do the color enhancement, to bring out these features which are otherwise difficult to see. But what this is showing is that Saturn has giant storms. The one in the left-hand corner lasted very, very long time, several months. The baroclinic waves are a genuine part of the atmosphere, come and go, and so are their cloud features. So Saturn has a smaller number of discrete features, but look at the right-hand corner. That really is an extraordinary feature. You can actually make out the edges of the hexagon, and the dots are individual storms. Some of those storms are pretty near the size of the United States. They are massive. The actual size of the hexagon, you could actually, it's much greater than the diameter of the Earth. It's more than the Earth could be lost in that. So if you put these two things together, what this has told us so far is, if you take Jupiter and map on the zonal velocity, the wind speeds, which we've obtained by tracking the clouds, so we did this by computer techniques, you can see the very strong zonal jet, the way in which the direction reverses at the boundary between the belts and the zones, and how Saturn has slightly stronger winds and in fact is much broader than Jupiter. So we're already learning that, looking at those two planets, Jupiter has fast winds, Saturn has faster winds, and a much broader structure. So our questions are beginning to build up. As we move on, we go to Uranus. Uranus really was an unknown. And if you look back, you'll find that Voyager is the only space mission so far that has been to have a good look at Uranus and Neptune. And for my discussions with colleagues around JPL, there isn't a discrete mission being planned for this, but it has raised up a few questions, some of which we can address by looking at the observations made by Hubble and other telescopes. On the left is Uranus. You may say, gosh, isn't that exciting? Not a feature there. It's as bland can be. So what we did on the right was actually construct a picture using red, using green, using blue, using UV, using green, using blue. And that was able to bring out the feature. Now remember, Uranus is oddball. It's been zonked by something in its lifetime, turned right over. It's 98 degrees over. In other words, the South Pole is looking at us, and you can see that there are zonal features. In 1985, when this picture was taken, you may say, well, you meteorologists must have been pretty bored, not much to see. But look what happened. These are pictures taken from Hubble from 2003 to 2007. And look, those zonal features are showing discrete clouds. So somehow, here is an object which has virtually no internal heating. It has about 300th of the amount of sunlight that we receive at the Earth. So in other words, it doesn't have any real solar energy. It's somehow dynamic. And that's another question. Why should it be dynamic? And it's dynamic sufficiently to produce discrete clouds on a seasonal basis. Voyager turned up, it looked pretty dead meteorologically. And now we can see, tracking it some 20 years later, there are features there. So already, like all things that we do as good scientists, we start with a question and we end up by answering that question, having an awful lot more to address. And we are. The list is getting longer as we speak. And we go on to Neptune. Now, we got even further. We've only got 1/900th of the sunlight that reaches the Earth. So it's got to have, so the question was, surely this is going to be a pretty dead object with nothing really exciting happening. But instead, we find that Neptune has the fastest winds anywhere in the solar system. It is incredibly dynamic. It has cloud features which are really extraordinarily active. You've got discrete storms, as you can see, a big dark spot, which again, we have anticyclonic storms. On the left-hand picture on the side, those are methane ice crystals, and they're probably about 75 kilometers above the main clouds. So here we are, we've gone even further out, a planet which does have a small amount of internal heating, about twice that it receives from the sun. So remember, Jupiter has 4 times, Saturn, again, a vast amount of internal heating, Uranus, nothing, but has some seasonal clouds, and now Neptune has other cloud features. I mean, if you look between 96 to 98, again, you can see that clouds come and go over this period of time. We've been able to do this using Voyager pictures, Galileo pictures, Cassini, Hubble, and of course, ground-based as well. So what can we expect? And if you look again, this is more recent over Hubble, you can see a discrete cloud feature taking place on Neptune. So the puzzlement is, Jupiter, we have already known was dynamic. Saturn has got these peculiar hexagonal features at the polar regions to add with discrete storms. Uranus has got seasonal clouds, and even Neptune has got features as well. How can we possibly explain it? Well, it comes to a time of, can we actually do anything with modeling? There have been some incredibly good models developed. And this is one example. This is done by Gareth Williams at Princeton, and this was done in the 80s. And I show this as an example that as the model develops, you can see the zonal structure developed. Now, there are 2 things that we've got to bear in mind. Is go back to the very first picture I showed you of the Earth. And there were discrete features which will constrain our weather systems, our continents, our oceans, and those changing land masses, and indeed the ways the sun alters around the year, those are all constraints on our weather systems. We're talking about planets which are totally gaseous, which are spinning. Their heating and cooling is not so differentially modified as the Earth. And so we have a more unconstrained weather system. And we're left with basic questions like, how deep is the weather? Now, how deep are the other weather systems? Are we dealing with a shallow system or a very deep system? And you know, by going down and looking at the sea around the Bay of Bengal, how the waves vary between what you see around the edge of the shore and what actually happens out at sea. You don't see gigantic storms, cloud waves way out in mid-ocean, but you do see some pretty large waves coming in towards the shore because the surface is affecting it. So far, as people have wrestled with some of the constraints, they've not been able to produce features like the red spot and such like. Some of the zonal motions are being established, but some of the basic questions are left there to look at. So what we can do in the future, there's a huge amount of modeling to be done. So those of you who are good at fluid dynamics and have good understanding of these processes, there is a mass of things to address. I'm going to show you, this is just an example of how we're getting some data now. The mission Juno is looking very much, obviously, at Jupiter at the moment. And because it's looking at the longer wavelengths, the radio wavelengths, it's able to penetrate the atmosphere much more deeply and see down to what's going on. Lightning storms have been seen. We saw them at Jupiter and Saturn, as you would expect. You've got irregularly shaped cloud particles in the ices in the upper layers, and you expect the charging to take place. So we can get some indication of the deeper layers through microwaves, the thermal infrared with good telescopes, either on board an observatory like Hubble or Webb that's coming up, or from telescopes like the Gemini one in Hawaii and in Chile, can look down deeper into the atmosphere, while the orbiting telescopes look at the higher levels. This would give us information at different parts of the electromagnetic spectrum, and therefore at different levels in the atmosphere. And what we need to do, you cannot solve atmospheric dynamics with a single picture. Dynamics is motion, a picture is a still. So we need to look at this over time. Personally, I think to actually study Uranus over time is going to be a fascinating object. These seasonal variations were a tremendous surprise. So if you bring this lot into and draw a conclusion, look at Jupiter. It has tremendous number of belts and zones, lots of very active storm systems, the rapidly changing elements of the zonal motions, low wind speed. As you move further out to Saturn, to Uranus, to Neptune, the belt zone structure seems to decrease. The wind speed seems to go up. Saturn has very fast winds, Uranus not quite as fast, Neptune extremely fast. So what does the depth of the ocean do, the depth of the atmosphere do to this? Does this imply that Jupiter has a deeper set of deeper active atmospheric environment than the others? Who knows what's taking place? So these are some of the things that we should be thinking about. So I thought I'd put together for you some questions. I don't expect to have the answers by the end of the morning, but these are things that we can think about. So the obvious question is, why are these planets bounded? Their chemistry is all muddled up. You can't imagine that the chemical elements are mixed up in some inhomogeneous manner, but they're being stirred up in a particular manner. We want to know what controls the wind speed. What controls the width of the jet? Look at the jets around Jupiter. Some of them are quite narrow. Saturn, they got broader. Uranus, we can't really see them, and Neptune, we can't see them either. But Jupiter and Saturn, there's clearly some interesting there about the width of the jets and what actually is taking place. And why are these things so stable? If you look back through history books, and I love collecting old books about astronomy and looking at old pictures, centuries and centuries are always shown these banded structures. Remember, Jupiter and Saturn actually are naked eye objects. There was a beautiful conjunction which you would have seen earlier in the year. So we've got the question of why the devil are they banded? What controls their speeds? Why is everything so stable? But where do they get their energy from? We have internal heating at Jupiter and Saturn. We don't at Uranus, yet we have some interesting things going on, and we certainly don't, and we have internal heating at Neptune. And what can we account? How can we really account for the things that we look at? We've tried, there have been some excellent attempts with the modeling. Gareth Williams is one, which I've mentioned, and others, which have tried to reproduce what we see, not always terribly successful. But does it imply that there's a different depth into the active level of the motions of the atmospheres of Jupiter compared with Saturn, compared with Uranus and Neptune? We need to be able to alter these parameters in our modeling technique. And how far do they extend into the fluid interior of the planet? This is the whole question. We would love to be able to measure deep within the atmosphere. Unfortunately, one of the problems is how long can any set of instruments being jettisoned in there of a spacecraft survive and be able to send the measurements back? It's not something we can do like fishing and drop it over the side or anything like that. That is extremely difficult to actually be able to achieve. But perhaps we can do that in time with some radio measurements. And of course, the composition is important. Let's think back to the Earth's atmosphere. What powers our weather systems? It's actually and the convective processes coming out of water vapor. We have plenty of that around. 70% of our planet is oceans. The water abundance of Jupiter and of Saturn, huge question marks. We can't really find as much as we expected. This is one of the surprises of the probe that was put out by Galileo. They didn't find as much water as they were anticipating. So the composition of the deeper atmosphere is extremely important, not only for the whole question of those people trying to understand the origin of the planet, but also to understand the dynamical processes that take place. But then this must be the puzzlement. Working on Voyager, Jupiter and Saturn were, I wouldn't say known, but they were better known because we had books about them, we had plenty of observations about them. Uranus and Neptune were a surprise, and boy, was it a surprise when we got to Neptune. Uranus seeing nothing was one thing, but to go to Neptune and find it so dynamic. If I asked you before the mission, do you think we'll find anything interesting in terms of the weather systems on Neptune? I would say every one of you will have been joined me and said probably not, but we would have been completely and utterly wrong. That's always fun when you're wrong, because you can always turn something wrong into something which is right. It's defending something which is right, which is tough. But then as you get further out there, the sun is dropping off like 1 over the square of the distance. So there's precious little sunlight when you get out to Uranus, and even less when you get to Neptune. We went through a lot of hoops to be able to get the pictures back from out there. So what's the power source for Uranus? Got no internal heating because of the way it's been damaged throughout the collision, yet it still managed to produce some weather for us, perhaps seasonally, but even that's a surprise as well. And of course, what drives this seasonal variation? Is it the way it orbits around and the way the heat gets redistributed by this extraordinary internal structure, what actually takes place? These are very strange, peculiar objects. They never stop us pondering what actually takes place. This book on Voyager, which is one of my most recent one, it's not there to advertise it, it's just to show you that we do actually read from time to time. Just shows you that in the 50 years that I've been involved with these missions and the whole question of space exploration, we've got some very basic questions to answer. But let's go back to my original comment. What was the driver to get involved? We wanted to understand about our storm systems on the Earth. We want to understand how these features interact. We're certainly looking at Uranus and Neptune and Jupiter and Saturn as natural laboratories of which we can study weather systems, and we can study oceanography too. They are remarkable places to work, and will give you tremendous number of research studies to do in the future, whether you're a mathematician, whether you're a physicist, a computer scientist, or just an astronomer, or an astronomer with your telescopic observations. There's plenty for you all to do. So I hope that has been of interest to you, and we'll show you some of the delights you can actually get out of looking at the weather systems of the planets in our outer solar system.
Thank you, sir, for your wonderful presentation. So we have student with us in our webinar. So we have got few questions in the chat box. So can you see those questions, or can I read it out?
Right, okay.
Okay. The first question, so can there be life somewhere in the solar system outside Earth?
Oh, indeed, that the question is define life, and the answer is yes. There has to be microbes. There have to be the infinitesimal steps towards it, and these have got to be the drivers. Who knows what's floating in the cloud tops? Because what's in the cloud tops of these outer planets has been brought there by other objects And Titan has got to be, which is an Earth in deep freeze, is clearly what one object that we can look at. I will be the probability of us being the only area to have life is just mathematically impossible. There has to be something elsewhere. There won't be people like you and me, and there won't be Martians running around with a big welcome sign with all these spacecraft arriving on Mars, but there will be the building blocks, and that's what we're looking for, because we're looking at these very strange objects.
Okay, thank you, sir. We have another question from our student Tushar Kumar. So question is, how can you tell a black hole made out of antimatter from a black hole made out of?
Say that again.
So okay, so how can you tell a black hole made out of antimatter?
Can did you say black hole?
Yeah, and made out of matter.
Oh, well, that's outside. I'm not a black hole specialist. I can't answer deep astrophysical questions. I'm only a simple meteorologist.
Okay, thanks for your question. You can ask another question. So how does a supernova completely destroy a star?
How does
a supernova completely destroy a star?
Let's get this. Whoops. That's better. That's right. So the storm systems are going to be how they dissipate. I think again in the Earth they dissipate because the storms run across on land and they move through their energy support. They lose their water, the loss of water and the friction aspects will break down the features on the Earth. Why these storms break down on the other planets is a question. It comes back to where does all the material come from? And I think that this really is the puzzle. There are lots of very fundamental questions. Those 10 questions, if you can answer any one of those, boy, you've got a fabulous career in front of you. They're nice, deep ones to think about.
Okay, sir. We have another question from Nadim. So, sir, does the wind flow or storm in each planet has any influence in their rotation?
No, this is all. That's an interesting. How do they? It's almost like a spin up. You know, it's a bit like looking at the computer models. If you look at that computer model by Gareth Williams, everything was there in a sort of hazy state, and the spinning motion, which will be there from the angular momentum. If you think about going down on the seashore with a handful of pebbles and you throw them out, they all start to move and they rotate. And it's just that conserved angular momentum that has got the spinning, which actually the materials there then start the rotations and then get into a stable state. But standing on the seashore tells you an awful lot watching the waves. Just throwing a handful of pebbles, that again will answer those questions quite directly.
So thank you. So,
hello, I have one question. Can you hear me?
I can hear you beautifully, Tamo. How are you? I could hear you.
Hello, I have one question.
Yeah.
Can you hear me, Dr. Garry?
I was hearing him. Who is he called?
Kamal Bashak from Kolkata, maybe. And so
Yes, sir.
yeah,
so
you can
I have one.
question.
Yes. So I have one small question that students they ask one question, that what if in very short, if I ask you that what is the fundamental difference between the atmospheric structure in Jovian planets and terrestrial planets? In very short, what should be the answer, sir? That is my question.
Well, the big difference is, of course, their composition, and of course we have an atmosphere which is a nitrogen atmosphere with water vapor and carbon dioxide very much mixed up. There's a hydrocarbons, hydrogen helium atmosphere with all the primitive hydrocarbons, and the Jovian atmospheres the question is, they go on and on and on, very, very deep. We are just scratching around at the top. So it's the compositional difference. You're looking at primordial atmospheres in the major planets compared with what you have on the mature terrestrial planets.
Okay. Okay. Thank you, sir. Thank you.
Thank you.
Thank you, Tamal Bashakda, for joining with us. So, dear students and viewers, if you have any more questions, you can ask.
I've silenced them all. It's wonderful to be able to talk to you and interact in this way so far away. You'll make you look at the weather differently. And if you ever get a chance to look at some of these movies, they are tremendous, I can tell you. But particularly watching them interact. I noticed looking at the weather, there is a huge storm over Mumbai at the moment. So I won't say it's coming your way, but sadly it is.
Yeah, yesterday we have faced,
Yes, actually, yes, there is a big loss. Yes, it was devastating. Yes,
yeah, in our
loss
part
of life and properties, lot of them.
Yeah. I've been in your part of the world in a monsoon. I don't wish to do it again.
Okay.
Okay, sir. So thank you for your wonderful presentation and discussion session, sir. So as we don't have any more question, we can conclude our discussion session. So I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. It is a very great webinar with you. I think the students have learned a lot of things about our planetary system and the weather system of different planets. So thanks again for your wonderful time with us.
Well, thank you very much. And to any of you watching, if you have things you want to ask me, you have my email address, email me. It'd be lovely to hear from you. Keep up your good work, and perhaps we'll talk again at some other time. It's been a pleasure to come to Bangladesh, and without getting jet lag too. So it's been a great
of course. After the COVID, I'm pleased to invite you in our beautiful country. And in my university too.
Well, it'll be a delight to be close to you, because you probably, if you look at my extraordinary career, yes, I have all my science background, but of course, as a businessman, I'm always advising businesses and governments and such like. So there are many ways that people like me could be helpful. It's been a pleasure talking to you all. Thank you all so much, and thank you for making this possible. I've enjoyed it.
Thanks, sir.
Yes, one more thing, Dr. Pretam.
Yeah,
yes.
thanks.
So sir, Dr. Garry, I just one very interesting talk. So I am thinking that very soon in future, I also want to invite you to our university for webinar.
Of course.
Well, if you've got my email address, send me an email and we can talk. Where are you, Tamil?
I'm from Kolkata, Amity University, Kolkata.
Oh, I know Calcutta very well. Yes. I've been to Calcutta. I know it well.
Okay.
My
Okay, that's great.
In the war. So
Okay.
it will be a delight to come to India. Keep safe and for this terrible virus, please.
Yes. Situation is very terrible. Yes. Yeah, thank you, sir.
Thank you very much indeed.
Thanks all for joining with us, and thanks, sir, for giving us this opportunity to arrange such important webinar with you, sir. So
thank you very much indeed. It's a great pleasure. Bye-bye.
Bye, sir.